Okay, let's get started. Today we're going to do some work with thermodynamics. And as a student pointed out in an email to me last night, I yet again chose two problems that have a little calculus aspect for the homework by accident. That's what they were all chosen at the same time, so apparently I made the mistake at the same time. So we'll go through on how to do those, and for you guys, it'll be super easy. For other people, it's not quite as easy. So there's some things here that are just going to look like review and some that don't. So let's start with what looks just like review. The first law of thermodynamics. Energy can't be created or destroyed. And so we talk about U, that internal energy, Q, the heat added to the system, W, the work done by the system. And so we have this energy balance equation up here that just says the change in energy is equal to the energy you add minus the energy you take out. I added here one more definition, entropy. Now, I will lecture some about what entropy means in class tomorrow, but this is where we are going to have entropy first enter our reality of physics. So entropy, you guys have probably all studied entropy in some way or another, right? And I'm going to define it carefully tomorrow, but I want to make sure people at least have an idea what entropy is before we get started. So who would like to offer a definition that they know for entropy? Mr. Maxwell.
Measurement of disorder.
Okay, measurement of disorder. That's what virtually everyone knows for the definition of entropy. So if I were to take an example of, I don't have a deck of cards here. Well, sure I do. I have my playing cards with all of your names on one side and my business card information on the other. So if I have them like this, that's one option. Or if I have them like, I hate to do this. If I have them like this, it's another option. How would you compare the entropies of the two? Okay, this one has higher entropy. Why? Okay, now, when we actually get down to understanding entropy, there is a mathematical equation for entropy. This equation right here is an equation for change in entropy, but there's actually a mathematical equation that says the entropy is equal to K natural log. Some books use omega, some use W. I'm going to use omega so it doesn't look like work. That's the actual mathematical equation for entropy. Has anyone seen that equation before? Generally, the answer is no. And to do this equation, to use it, you have to know what things are. So what's K? Well, K is the Maxwell-Boltzmann constant, 1.38, whatever, times 10 to the, was it minus 38 joules per Kelvin? Plus 23. Anyone? It's not 38. I can't be right.
Negative 23.
Negative 23. Yeah. I should look up these constants from time to time. So that's just a constant. But the tricky part is that's the number of microstates in the macro state. And when you say that, there's some, that's a singular macro state. There's some explanation that needs to go on. If you just write that down or say those words and move on, all you've done is confuse people. But if we can understand what these things are, well, it starts making more sense.
Yeah,
it's okay. So I still have the cards played out here, but let's go with something simpler. Back when I was in college, I went to Loma Linda University, La Sierra campus. And there is an establishment about 3 hours drive away, depends on how fast you drive, could be 4 if you're a slower driver, where they specialize in studying statistics. And so when we got to be seniors, we decided that we needed to go study statistics. And before you go study statistics there, we probably figured we should practice some on our own. And so one of my friends brought in a big old craps table, which we kept in my dorm room. And then we would practice playing craps. So when we went to the University to study statistics here in Las Vegas, why, we would know what we were doing. And then I got in trouble. Fire alarms. Deans come in, you're still asleep, and there's a big craps table. So what does this have to do with entropy? Well, anybody here know anything about craps at all? Nope. Okay, good. We won't explain the rules then. But you roll 2 dice. And everything in craps is like, it has some bets you can make that are actually fair bets, unlike everything else in Vegas. And so it's your best chance, they say, to make money if you are so inclined, which, frankly, I don't have the kind of money to be that inclined. So what you look at is, what are the odds, the statistics involved with rolling 2 dice? And all of the odds, like when you buy a number, they actually pay out the true odds. That's where you have your advantages. Well, we don't want to look at this from a physics state. So from a physics look, when you're rolling 2 dice, you're going to have the macro state and the micro states. What's the lowest roll you can get with 2 dice? 2. And how can you get the roll of 2? So you have 1 die with 1 pip and the other die with 1 pip. Whoops. I put those on the macro side. There we go. So the macro state here is 2 because you had 2 pips showing. The next one, of course, is going to be 3, having 3 pips showing. But how can you roll 3?
1 and 2 or 2 and 1.
So those are 2 different microstates that have the same macro state. And if you keep going, of course, to get 4, you can have 3 different ways of rolling 4. A 1 and a 3, a 2 and a 2, or a 3 and a 1. And so you can keep track of the number of microstates. And of course, I'm just going to put the number of microstates. So I'll put our symbol omega there. So there was 1 microstate in the macrostate of 2. 2 microstates in the macrostate of 3. And just keeping going with the numbers. Okay, things get closer together at the bottom. It's, kind of like length contraction we'll learn about. Okay, so 1, 2, actually, let's put the numbers right next to it, just so we have the numbers easily identifiable. 1, 2, 3. 6 ways to get 7. A 1 and a 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. To get an 8, we start cutting off. We can only still 2 and 6. And so it turns out we have 1 less. So it goes back down. Now, if you're playing craps, what's the most likely roll? 7. What are the odds of a 7 coming up? I wish. It's 6 out of 36. If you add up all of those numbers of microstates, you have a total of 36 different microstates. And you have 6 microstates that are 7. So there's a 1 in 6 chance of that 7 coming up. So if you're playing craps, the opening roll, if it's a 7, woo, winner. So 1 in 6 times you win right off the bat, statistically. I think 11's also a winner on opening roll. I didn't pay enough attention to the rules. After that, though, 7 is craps. You lose if 7 comes up again after the first roll. And since it's the most likely outcome each roll, chances are you're going to lose money along the way. So how does this play into our thermodynamics? Well, we can just take these numbers and you say, okay, if I take the natural log of 1, what's the natural log of 1? 0. So that means that my entropy, and let's make entropy purple, my entropy is going to be 0 if my number is 2. And the entropy for the number 3 is going to be k times the natural log of 2, which is going to be bigger than 0, but it's, k natural log of 2. And if we keep coming down, my entropy is the highest at k natural log of 6 when I get to 7. And then it goes back down again to an entropy of 0 for 12. So we can actually assign entropies to these numbers. If I were to graph the number of microstates as a function of the macrostate, the graph is really boring. Goes like that, right? But we can read this as a probability. The highest number of microstates is the most probable outcome. And statistics sets up entropy as being a number proportional to that probability. So the higher the entropy, the more probable the state is. And now you start to wonder, now what is that real second law of the disorder thing? Let's imagine instead of having 2 dice, that we were playing craps with 2 billion dice. If you're playing craps with 2 billion dice, of course, your options are going to go between 2 billion and 12 billion. For the result you can get, is it going to have this nice straight lines for the number of microstates for each macrostate building up to the center? No, it's not. You're going to have a lot more states that have a number close to the average between those two, close to 7 billion, than you would have down here. So if you have a lot of, that color's not going to work. If you have a lot of dice, it becomes a function that looks a lot more like this. And the more you have, the stronger that peak gets. And so if you were to take something like a collection of all the atoms in this room, and you look at the statistics for all of the different possible pressures, temperatures, and volume, you find that you have a statistical situation that says 0 probability, or virtually 0, until you get to one state that has a virtual probability of 1, and then the rest are back to 0. And so when we're talking about entropy, the second law says the most likely outcome is the most probable outcome. The one with the highest entropy is the most probable one, and that's what's going to happen. So the second law is actually a statistical law. It doesn't say what has to happen, but it says because the odds are so significantly in the favor of this, it's what's going to happen. So that's what entropy really is, and I spent a lot more time describing it than I intended to. So now if I come back to this, you can say, why is this a lower, it's a higher entropy, a more disordered state? Because there's more ways that I could arrange the cards like this than there are to have them all in a row. But you can take something like, say you're dealt 5 cards. And so I have here Carrie, Sandy, James, Brady, you're out, and Brandy. And so I take these 5 cards and I can say, well, is this a high entropy or low entropy hand? If we were playing something like poker, if I had 4 aces, I'd say, oh, it's a really low entropy hand because the probability of getting 4 aces is very little, right? But what if our game was that we wanted to get, I want to take all these cards and I want to pull out the 2 of diamonds and the 4 of, I was going to say 4 of jacks, shows how well I know. The 4 of clubs and, the ace of spades and, I named 5 specific cards. If I pull those out, I would say, well, That must have been a highly ordered hand because it was what I was looking for. So it kind of depends on what you're looking for, how you describe if it's ordered or not. And that makes the whole ordered thing a little more confusing. But if you understand what that entropy is, it's basically saying how likely was that outcome. And the higher the likelihood of the outcome, just based on statistics, the higher the entropy, then it makes perfect sense. So now let's look at our calculations. Let's go to page, 2 of the lecture. Actually, I have to stay here. I can't go to page 2 yet. Because I put ds is equal to dq over t, but I put a funny slash there. I put that funny slash because notice up here we have a delta U. Delta, because we can, of course, have a change in internal energy. Because objects have internal energy. But there's no delta Q. There's no delta W. Technically, you never should have a delta Q or a delta W because a Q is a change in energy. It's a transfer. You don't have a change in your transfer. You just have how much energy was transferred in the end. So when we want to make a differential equation, right, this equation, if we were to take into calculus, we would tend to write this as du is equal to dq minus dw. But work and heat, that's not really correct. We call them inexact, and so the way we indicate that is by putting the slash on the d. Inexact or improper, it might be improper is the word. Yeah.
Couldn't you just substitute in the definition of heat for that? And then you could have a dt or something?
We'll be doing that.
Okay.
Good thinking. Okay, so that's why you sometimes see that slash. Oftentimes, we don't even put it in there because we treat it just like we would any other differential. But there is a reason you sometimes see it, or I've seen other books that do this kind of D, but in physics, we reserve that D for other things. So just keep it simple, the D with the slash. So the change in entropy. So the equation down below here was the actual entropy. The change in entropy is defined as the heat divided by the temperature. Now, for general physics purposes, we tend to just write this as heat over temperature and say we're done. But it's only correct if the temperature is constant. If it's not constant, then you have to do integrals. Hence, problems 1 and 2 in your homework, you have to do the integral. Now, it's really, really simple integral. And for the other students, I'll give them the equation. But let's now move forward. Calculating thermodynamic work. Work is integral of force dot dx. We looked at the pictures in class yesterday talking about how pressure relates to the force on a piston. Since force is pressure times area, I can rewrite my equation. Work is force, pressure times area in the direction going into the surface, dotted to dx, the direction the surface moves. And we get this simple integral that work is integral of pressure dV, since area dx is going to be dV. This actually, if you think it through, this is actually a legitimate, in all cases, derivation, as opposed to what we did in class, which was specific. It doesn't look very different, doesn't look very complicated. But what you're saying is, for each little piece of area, my force is going into the surface and the dx is perpendicular to that normal, well, same direction as the pressure then, or as the force. And so dV is just going to be that A dx. And it's legit. So let's look at the different processes and how our variables change. So isochoric process. What does the term isochoric mean? Constant volume. So if I have a constant volume process, then I'm going to have work is equal to integral of P dV going from A to A, right? Because there's no change in volume. And that's equal to 0. So the work is 0 for the isochoric process, which means that my first law is just change in internal energy is the heat. And using the isochoric version of heat, that is heat is equal to number of moles times the constant volume, isochoric, molar specific heat times the change in temperature, I can put that in my differential term here and then do essentially what Jonathan had suggested. I can now calculate the change in entropy for an isothermal or isochoric process is equal to the integral of ds, of course, by definition, which is going to be the integral of dq over t. And now using that dq, that's the integral of ncv dt over t. What's the integral of dt over t? Natural log. Now keep in mind, this has limits, temperature initial and temperature final. So when you put in those limits, and so this is our change in entropy for an isochoric process. Now, in your homework problem, you had water, not a gas, water. So if you're using water instead of a gas, you're not going to use this constant volume equation. For the homework, you would use dq is equal to mc dt. And how would you get a different value for the change in entropy in that case? What's different? It's just that you replaced mass times the specific heat with number of moles times the molar specific heat. So it's just going to be mc, natural log of temperature final over temperature initial. So you have, go ahead.
This is only for isochoric?
Well, the one in green was only for isochoric. The one in purple is if you have a material, solid or liquid, which is actually pretty close to isochoric still, that's changing temperature as you put heat in. So it wouldn't apply to changing phase, right? It applies to changing temperature. If it's changing phase, then you're going to have an isothermal process. And so the isothermal result is what you would use if it's changing phase. But the homework problem wasn't changing phase. Now, interesting to note, the change in internal energy, it doesn't have to be a monatomic ideal gas, it just has to be an ideal gas, is NCV times the change in temperature. So for any ideal gas, if it's isochoric, you know how the internal energy is changing. Go to the isobaric process. For the isobaric process, that means constant pressure. And so we define a different molar specific heat if we're doing a put in energy and keep the pressure constant, how much does the temperature change? Compared to if we put in energy, we keep the volume constant, how much did the energy change? So it's a different value for that molar specific heat. And so we have, I mean, this looks exactly the same except for you change CV to CP. And so if you calculate the work, well, the work is just darn trivial, because if the pressure is constant, then you do the integral of PdV, that's the integral of dV from starting to ending, and you get the work is pressure times change in volume, which of course is what we learn in the algebra-based class to begin with. And so we have a relationship here. Pressure times change in volume is equal to NR, change in temperature, complete agreeing with the ideal gas law as long as the pressure is constant, which is where we started. So notice the change in internal energy is now more complicated. Delta U, the change in internal energy, is equal to NCP delta T minus NR delta T, since the work was NR delta T. And so I can put this delta U is equal to N times CP something to tell me how the internal energy is going to change if I change temperature. That just has to do with the number of moles and delta T. Not the final, but we're getting close to the end, thankfully, because I'm not going to run out of time after all. For an isothermal process, now the temperature is constant. So if the temperature is constant, then for an ideal gas, I'm going to have, PV equals nRT, and the internal energy, U, is proportional to temperature. That's not proportional. U is proportional to temperature for an ideal gas. Right? The internal energy is proportional to temperature. So if it's isothermal, that means the internal energy is not changing. That delta U has to be 0 if it's an ideal gas. And so in that case, and notice this equation right here. This here is for a monatomic. Monatomic sets that 3/2 nRT. If it was diatomic, depending on the temperature, it could be 3/2 or 5/2 or 7/2. Remember us going through that? Energy split in the different, but it's still going to be proportional to temperature. So for any ideal gas, if the temperature is constant, if it's isothermal, the change in internal energy is going to be 0, which means that your heat and work are equal to each other. So your heat is going to have to be equal to the same thing as the work calculation, integral P dV. But since PV is nRT, I can just solve that for P to get P is equal to nRT divided by V, and I put that in for the pressure. Why do I do that? I'm sorry. Why do I do that? I do that because I want to get my integral into just one variable, into volume, since I have a dV. And so now if I do this integral, I have my work put my limits there in the last one. I'm kind of lazy. I'm putting the limits down, aren't I? Because technically I should have them on everything. If I do that, again, integral of dV over V is just going to be natural log of V. So my work is equal to nRT natural log of V final over V initial. If you like, you can replace nRT with PV. Pressure times volume is going to have to stay constant, so you could use initial pressure and initial volume, or final pressure and final volume. It'd still work out because the temperature is constant. So those are equations to tell me what the work is if I have an isothermal process. Well, what about the change in entropy if it's isothermal? Remember, I had ds was equal to dq over t.
So there's no change in entropy, right?
No, not no change in entropy, because I do have a heat. But if the temperature is constant, I can bring that out. 1 over temperature integral of dq, which is just equal to Q over temperature. And since I just calculated that work has to be equal to Q, then I have my change in entropy is equal to nRT, natural log of V final over V initial, all divided by temperature. And so we can now calculate the change in entropy for an isothermal process. And notice this entropy does change, even though the temperature remained constant, because of heat flowing in or out. Go ahead.
Is that a negative sign, or is that just part of the integral?
You talking about my mistake? You talking about this?
Yeah, and then is it a D0 or DQ?
That's a Q. That is a more important thing. Let's pretend that slash that was in the wrong place was supposed to be there, and two wrongs make a right. It's a good pretending thing, not a realistic one. Okay, so we've looked at isothermal process, the isobaric. I didn't actually do the calculation here for the change in entropy, so let's do that real quick. That's a Q. So for this case, that would be equal to NCP integral dt over t. And just like we had in the first one, delta S is going to be NCP, natural log of temperature final over temperature initial. So we've calculated the entropy changes now for everything but one type of process. We did it for the isochoric, the isobaric, the isothermal. What's the last one? Okay. The final one is going to be the adiabatic. Adiabatic has another name for an obvious reason. Can I change now?
Yeah.
Okay. Has another name for an obvious reason. What does adiabatic mean? It means Q equals 0. And since ds is equal to dq over temperature, if dq is 0, what is ds going to be? 0. So I'm going to end up with the change in entropy is 0 for an adiabatic process. So there is another name for adiabatic process, and that is equals isentrope. An isentropic process is a process in which the entropy doesn't change. So an adiabatic process is isentropic. So the meanings are delta S equals 0 for the right-hand side. For the left-hand side, Q equals 0. So they have technically different meanings, but they describe the same situation. Notice, so work can be calculated. I left this one for the rest of the class period. How do we calculate the work for an adiabatic process? Adiabatic process, we know that, of course, delta U is equal to Q minus W. Right, delta U is minus work. And so if we take this equation that PV raised to the gamma is constant for an adiabatic process, I didn't go through the derivation of that, then I can say that work is equal to the integral of pressure dV, right? And since PV raised to the gamma is constant, that condition tells me that I'm going to put P naught V naught raised to the gamma is equal to PV raised to the gamma. So the pressure I start with times the volume I start with raised to the gamma is equal to pressure times volume raised to gamma at any moment. Why do I do that? So I can solve for P in terms of volume. And now I'm pretty much in business because I can put that into my work calculation. What do I get when I do my integral?
gamma times the natural log.
Not natural log, because that's v raised to the gamma. Okay, I think she's right, but I'm going to do it the long way to make sure. So the integral of v raised to the minus gamma dv, right? That's how I make sure I do it right. And so our rules for integration is you raise the power by 1 and divide by the new power. So that's going to be v to the minus gamma plus 1 divided by, and I'm going to put it as 1 minus gamma because it's quicker. And that should be something pretty close to what you said. Oh, that's beautiful, isn't it? Just beautiful. How can I make this any harder on myself? There's my constant stuff. And then I'm going to have, notice it's I like to make this look a little, well, at some point I like to combine what I can with the V's. It was minus gamma plus 1 on top, and so when I put it on bottom, I have to change the signs of both.
The one is still positive.
It should, you're right. Yes, I changed neither. I just changed the order, didn't I? Excellent. Thank you, Carrie, for keeping me straight. Okay, yeah, that's good. Good correction. So let's just expand this out and then see what we can do. I think I put that in right. Now, if you look at this, I could rearrange this further. Because P naught V naught to the gamma is equal to P final V final to the gamma. Did you have a question, Jonathan?
How did you get the v to the gamma minus 1 in the denominator?
Okay, I had V to the minus gamma plus 1 in the numerator, right?
Right.
And so I did it wrong the first time, but I flipped the sign, so made the opposite of this sign here and put it below.
Okay.
So I just raised it to the minus 1, if you will. Oops. I'm going to write the first one with finals. The second one with initials. And actually, this time I didn't forget. I'm going to put it at the end. So I replaced P naught V naught to the gamma with P final V final to the gamma in the first one. But now if you look at this, what do I get when I divide V final to the gamma by V final to the gamma minus 1? Well, it's dividing by 1 less than gamma. And so it's just going to be P final V final. So this turns out to be simple. So the work, it's actually a simple equation, surprisingly. But you have that factor of 1 minus gamma. Well, what is gamma? Gamma is the ratio of the constant pressure molar specific heat to the constant volume molar specific heat. I don't have the answer written here. Somehow I feel like I should have had 1 minus instead of, or gamma minus 1 instead of 1 minus gamma, but I don't think I made a mistake there.
I don't think there are any pressure finals, or there shouldn't be a PF anywhere in the equation.
Well, I substituted, okay, I didn't write it down, but I substituted.
Okay, that makes more sense.
I substituted this in to get that.
Okay, I'm slow.
Well, my work seems legit to me. I think I did it right. So the work, it was a more complicated calculation there, but it came out looking pretty simple for our adiabatic process. This is actually all I had prepared for today. I finished early after spending an extra 20 minutes or 15 minutes. First Aaron, then Gabriel.
So would a test question have to do with deriving it for the process that we're using and then plugging in the numbers that are given?
It could go either asking you to derive it, or it could just give you a situation like with the water problem. You have a homework problem that says you mix this mass of water at this temperature with this mass of water at this temperature, and what's the net change in entropy for that process. And so you would have to go through then and say, okay, change in entropy is ds is equal to dq over t, and go through the calculation that dq is mc dt, the thing that Jonathan suggested right at the outset, and do your calculation. Gabriel.
I'm just asking if you could scroll down to that body work.
Maybe I should have done Gabriel's first. Any other questions? There's actually a lot more calculus in thermodynamics than what we did today. There is a chemistry class going on this semester that's physical chemistry thermodynamics, where they are studying this from a chemistry perspective, but it's still studying a whole lot of calculus involved with thermodynamics. Because thermodynamics is statistics, and you have to use calculus along the way in those statistics. It's heavily math. Hence, it's kind of fun. Other questions? All righty then.